Today we will discuss about Hornblende Hornfels Facies. Now take up the Hornblende Hornfels Facies. Content, introduction, mineralogical limits, preliminary definition, important reaction, mineral assemblies, physical condition of metamorphism, and conclusion. The basis of pressure and temperature, we can divide the metamorphic phases into three types, mainly phases of low pressure, phases of intermediate pressure, and phases of higher pressure. Maya 0 originally recognized three different phases series. First, geolite, prehenite, pumpelite, blue schist, eclogite type. Second, a typical Barrovian type characterized by kyanite to sillimanite. And third, an Abukama type of green schist, amphibolite, gaulite characterized by paragensis, andalusite sillimanite type. The Abukama type is a name after the Abukama region in Japan, and it is similar to the Buchan type of Dalindian. The phases of low pressure are listed below in order of increasing temperature of metamorphism, that is albite epidote Hornfels Facies, Hornblende Hornfels Facies, pyroxene Hornfels Facies, and cyanidinite facies. The temperature of metamorphism increase from albite epidote Hornfels Facies to cyanidinite facies. The rock of Hornblende Hornfels Facies occur in contact areoles. They may be passed outward with decreasing metamorphic grade into albite epidote Hornfels Facies. In some areoles, they are seen to pass inward with increasing grade into the rock of pyroxene Hornfels Facies, such as the classic low pressure Oslo areoles Goldsmith 9011 and the high pressure zones adjacent to the major basic pluton, as such those of the Bushveld and Stillwater complexes. Elsewhere, the Hornblende Hornfels Facies continue to the intrusive contact. It is also registered by the mineral assemblies by xenolith and roof pendants. Rock of this facies also occur on a regional scale without any obvious relation to intrusive contact. For example, northeast of Scotland, Buchan type of metamorphism, pyroxene in Alps, rocky metamorphic belt Japan, and Khetri copper belt Rajasthan, India. Please see on the screen the intrusive gabbroic rock within the country rock. We can see the concentric rings all around intrusive body towards country rock. If suppose we will move from intrusive body towards outer zones, the temperature usually decrease, and vice versa. If suppose we will move from outward towards intrusive side, the temperature normally increase. And Hornblende Hornfels Facies usually occur in intermediate zone. Inward, we can find pyroxene Hornfels Facies, and outward, normally we can find albite epidote Hornfels Facies. We can see the important textures usually present in Hornfelsic rocks, that is Hornfels, where we can see there is no foliation present because there is a thermal baking, and we can see how the country rock is heated, melt and recrystallize. Because pressure is very low, so during Hornfelsic textures, the grains are usually very fine, randomly oriented. On the basis of this we can see or we can identify the Hornblende Hornfels facies with the amphibolite facies. If suppose we will compare the both facies, that is Hornblende Hornfels facies and amphibolite facies, we can observe certain important things. In Hornblende Hornfels facies, we can see andalusite present, which is normally absent on amphibolite facies. Similarly, the kyanite present and almandine garnet present in amphibolite facies are usually absent in Hornblende Hornfels facies. On the basis of zones, we can divide the amphibolite facies into 4 different zones: stolite zone, kyanite almandine zone, sillimanite muscovite zone, and sillimanite orthoclase zone. While in case of Hornblende Hornfels facies, there is no subzones. In amphibolite facies, we can see different schist, gneiss, and calcareous ultramafic assemblies, while in case of Hornblende Hornfels facies, the calcareous assemblies are very important, which will cover under chemographic relationship and important mineral assemblies. Mineralogical limits. The mineralogical assemblies of the Hornblende Hornfels facies differ from the albite epidote Hornfels facies in the development of Hornblende plagioclase. Anorthite percent varies from 25 to 40 rather than albite epidote actinolite, and in the presence of diapside and gracilorite bearing assemblies in calcareous rocks, presence of andalusite, cauderite, absence of epidote and kyanite, and rarity of almandine and stolite distinguish the Hornblende Hornfels facies from the amphibolite facies. The typical assemblies of basic Hornfels is Hornblende plagioclase, diapside may also be present, but seldom almandine or epidote, muscovite, biotite, quartz is usually present in peltic rocks. Andalusite and or cauderite appear mainly in rocks lacking potash feldspar. Sillimanite, but not kyanite, may take the place of andalusite. In the more aluminous peltic assemblies, pyrophyllite has not been recorded. Rocks formed from siliceous, limestone and dolomites typically consist of combination of calcite or dolomite, tremolite and diapside. Important reaction. The beginning of Hornblende Hornfels facies is marked by the disappearance of chlorite in the presence of quartz and by the first appearance of the following minerals: diapside, phosphorite, gracilorite, andradite, cummingtonite. The reaction involved in the formation of these minerals are as follows. Reaction 1: tremolite plus calcite plus quartz give rise to diapside plus CO2 plus water. Reaction 2: chlorite plus muscovite plus quartz give rise to cauderite plus biotite plus aluminosilicates plus water. Reaction 3, chlorite plus andalusite plus quartz give rise to cordierite plus water. Reaction 4, Al-rich chlorite plus quartz give rise to gaderite plus cordierite plus water. Reaction 5th, chlorite plus tremolite plus quartz give rise to hornblende plus anthophyllite. Reaction 6, chlorite plus tremolite plus epidote give rise to hornblende plus water. Reaction 7, epidote plus calcite plus quartz give rise to gracilorite plus andradite plus water. Reaction 8, talc give rise to Mg anthophyllite plus quartz plus water. Reaction 9, tremolite plus calcite give rise to diopside plus phosphorite plus CO2 plus water. Reaction 10, tremolite plus dolomite give rise to phosphorite plus calcite plus CO2 plus water. Mineral assemblages. See the ACF, AKF and CO, MgO, SiO2 diagrams on the screen. The peltic rocks assemblies, andalusite, cordierite, biotite, muscovite, quartz, plesioclase. Second, andalusite, cordierite, muscovite, quartz, plesioclase. Third, cordierite plus biotite plus plesioclase plus muscovite plus quartz. Next important assemblies is your basic assemblies, that is hornblende, plesioclase, biotite plus quartz. Number 5th is your hornblende, plesioclase, diopside, calcareous assemblies. Diopside, gracilorite, plesioclase, quartz, diopside, gracilorite plus calcite plus quartz, diopside, gracilorite, wollastonite, quartz. Number 9 is your talc plus tremolite plus quartz. Number 10, cordierite plus anthophyllite plus quartz plus biotite. And quartzo-feldspathic assemblies, quartz plus plesioclase plus microcline plus biotite plus muscovite. Muscovite and quartz are stable over the major part of the PT range. At high temperature site, the reaction muscovite plus quartz give rise to potash feldspar plus aluminosilicate plus water take place, which result in the coexistence of cordierite and or aluminosilicate with potash feldspar. The assemblies quartz, microcline, andalusite, sillimanite, cordierite, if associated with basic assemblies, hornblende, plesioclase belong to the hornblende Hornfels Facies. Although this is a characteristic assemblies of the pyroxene Hornfels Facies. Now, next important assemblages are silica deficient assemblages, which are calcite, diopside, phosphorite, calcite, phosphorite, dolomite and calcite, diopside, wollastonite only at maximum temperature of this facies, and diopside, phosphorite, tremolite, phosphorite, tremolite, talc, chlorite, anthophyllite, chlorite and phosphorite, spinel, brucite. Hornblende Hornfels Facies is important in the sense all the amphiboles usually present in this facies like tremolite, actinolite, anthophyllite, cummingtonite, gaderite, etc. If suppose we will compare the ACF diagram of albite epidote Hornfels Facies and hornblende Hornfels Facies, then we can see in albite epidote Hornfels Facies even hornblende is absent, while in case of hornblende Hornfels Facies, hornblende, cummingtonite, gaderite, anthophyllite present, Another important thing is the calcareous assemblies. We can see the calcareous assemblies which is usually present in Albite epidote Hornfels facies. Please see on the screen the diagram where we can see calcite, dolomite, tremolite, calcite, tremolite, quartz, which are very important. While in case of Hornblende Hornfels facies, we can see the important calcareous assemblies are grassolarite, dapsite, calcite, dapsite, grassolarite, plagioclase, calcite, dapsite, silica, as compared to Albite epidote Hornfels facies, because dapsite appear in Hornblende Hornfels facies as compared to Albite epidote Hornfels facies. If suppose we will compare the other basic assemblies, the basic Hornfelsic assemblies are particularly in Hornblende Hornfels facies, we can see the dapsite, hornblende, plagioclase, dapsite, hornblende, plagioclase, chlorite, biotite, plus minus quartz. These are the basic calcareous assemblies usually present in Hornblende Hornfels facies. While in case of Albite epidote Hornfels facies, we can observe the tremolite, actinolite, epidote, chlorite, plus minus quartz as a basic assemblies. If suppose temperature is higher, then usually whatever amphiboles are present, they change into pyroxene groups. In pyroxene Hornfels facies, there will be no amphiboles present, and if suppose we will compare the basic assemblies, then we can see the dapsite, hypersthene, plagioclase, that is your anorthite, is your important basic assemblies. The physical condition of metamorphism can be represented by the PT condition of metamorphism. The lower temperature limit can be represented by the following reaction: chlorite plus muscovite plus quartz give rise to corderite plus biotite plus aluminosilicate plus water. The reaction carried out by Hochberg and Winkler, the temperature is 550 degree centigrade 1 kilobar, 525 degree centigrade 2 kilobar. Another reaction is Al rich chloride plus quartz give rise to gaderite plus corderite plus water, which is carried out by Akela 1966 at 560 degree centigrade 2 kilobar. The upper temperature limit. The upper temperature limit can be designated by the reaction gaderite plus quartz give rise to hypersthene plus corderite plus water at 705 degree centigrade 1 kilobar, 755 degree centigrade 2 kilobar by Akela. Another reaction is gaderite plus quartz give rise to hypersthene plus anorthite plus hornblende plus water, 715 degree centigrade 1 kilobar, 770 degree centigrade 2 kilobar. This reaction carried out by Chaudhary and Winkler 1967. Next reaction is Mg anthophyllite plus quartz give rise to anesthite plus quartz plus water, 745 degree centigrade 1 kilobar, carried out by Greenwood 1963. These reactions therefore suggested temperature range between 500 to 550 to 700, 750 degrees centigrade for this facies. Pressure condition ranges up to nearly 4 kilobar, and upper limit is indicated by the common presence of andalusite and garnet, rarely absent. So, that is why we can say the temperature and pressure is varying from 500 to 550 to 700, 750 degrees centigrade, and pressure usually within 4 kilobar or less than 4 kilobar. The PT condition is responsible because on the basis of PT condition, we can decipher how the one facies is responsible with a minimum temperature and pressure and maximum temperature and pressure. Say for example, how the Albite epidote Hornfels facies change into Hornblende Hornfels facies, and later on how the Hornblende Hornfels facies change into pyroxene Hornfels facies. Metamorphism is always important to decipher the metamorphic facies as well as the grade of metamorphism. Particularly in thermal metamorphism, usually the temperature is higher and pressure is always less than 4 kilobar. The course content of metamorphic low pressure facies begins with the introduction, followed by the description of Hornblende Hornfels facies, the important characteristics minerals in this facies, the chemographic phase relations with the help of ACF, AKF and CO, MgO, SiO2 diagrams, and the mineral assemblages for the peltic, basic and calcareous rocks, and finally the physical condition of metamorphism during Hornblende Hornfels facies. The mineral reactions leading to the formation of gaderite and breakdown of gaderite and anthophyllite, and the formation of orthopyroxene provide data characteristics of low and upper temperature limit of this facies. The reaction Al-rich chloride plus quartz give rise to gaderite plus corderite plus water. The reaction carried out by Akela in 1966 at 560 degrees centigrade 2 kilobar. Another reaction is your gaderite plus quartz give rise to hypersthene plus corderite plus water at 700 degrees centigrade 1 kilobar, 750 degrees centigrade 2 kilobar. Mg anthophyllite give rise to anisotite plus quartz plus water at 745 degrees centigrade 1 kilobar, carried out by Ringwood 1963. Thus, absence of almandine and kyanite in low pressure environment of metamorphism suggests of less than 4 kilobar pressure or so during metamorphism of Hornblende Hornfels facies, and temperature varies from 500 to 550 to 700, 750 degrees centigrade. The Hornblende Hornfels facies is important because if suppose you will see the Indian example as well as the world examples, we can see the Khetri copper belt is very important economic deposit of copper, which is mainly formed by the thermal metamorphism, where the granite intrusion, if suppose we will see the academic point of view, usually one very important question is asked about the thermal metamorphism of calcareous rocks in all the examinations like UG, undergraduate examination, postgraduate examinations, and even in GSI, etc. Give a detailed account of thermal metamorphism of calcareous rocks. Then in that case, we have to summarize all the 4 different phases, that is Albite epidote Hornfels Facies, Hornblende Hornfels Facies, Pyroxene Hornfels Facies, and Cenidenite Facies only with the help of ACF and CO, MgO, SiO2 diagrams, and we have to describe only the calcareous assemblies. So, it will be very easy to understand with the help of ACF as well as CO, MgO and SiO2 diagrams, and we have to confine only on calcareous assemblies.